Alright, Miss Howard's Chemistry, Chemical Bonding, Lewis dot structures, naming compounds, and writing formulas, Unit 6, and I believe this is Part 4. Whew! Alright, we still have the same things we've been talking about. You're going to have to name the compounds. You're going to have to write the formulas. You have to construct electron dot formulas to illustrate ionic and covalent bonds. And if you have to illustrate them, you have to know what they are before you can make that illustration. You have to describe metallic bonding and how it applies to their characteristics, and you have to predict molecular geometry. Okay, so let's look at Roman numeral number 2, electron dot notation, and the Lewis structures. Okay, electron configuration shows how the valence electrons are arranged around the atoms. And remember when we just do one element, let's say we want to show the electron dot or Lewis dot notation for sodium. Sodium has one valence electron, so we have the symbol for sodium Na, and we put one dot next to it. The Lewis structures keep the dots to show the unshared paired electrons, and they use a line typically to show a shared paired electrons. Now, we can keep them all with dots, or we can simplify it later on and just use lines to show the shared paired electrons. So typically what the state of Texas wants you to do is it wants you to show all the little dots and how they're arranged when you have an ionic bond and when you have a covalent bond. If we use the structural formula, what that means is we don't waste all our time making all the dots. We just show the shared pairs of electrons, or the electrons that are between them. Typically, that's going to be obviously in the molecular bond. Okay, so here we have phosphorus. It has 5 valence electrons, and we have bromine, and it has 7 valence electrons. So here are the Lewis structures for the individual atoms. If we have a sodium atom, we have Na with 1 dot, but remember, that sodium is a metal, and it's going to become a cation, which is a positive ion. That means it's going to give that 1 electron away, and it becomes a positive ion. And that's how it's shown, Na with a plus, or it could be +1, or they might put the 1 first and the plus sign after it. Phosphorus, we have the valence electrons shown, and bromine, we have the valence electrons shown. Okay, let's go on. All right, so here's some examples of ionic compounds with the Lewis structures. What is a cation afraid of? A dog ion. All right, so the bromide ion. Bromine has 7 valence electrons, so if we're going to show the Lewis dot structure, we put 7 dots around it, right? But it needs 1 more electron to be stable, right? So it's going to bond with something, and it's going to take an electron from one of those metals. When it's in an ionic compound and it takes one of those electrons, we show that. Notice if you count, there are 8 valence electrons around it. We put the brackets around it to show that bromine owns those electrons now, and then we put the negative sign beside it. We could put just a negative, since it's a -1 charge, we could put just 1 negative sign, or we could put a -1 sign. So we need to make the brackets to show that the bromide ion owns all the electrons. This is important when we make an ionic compound, such as sodium chloride or sodium bromide that we're using here. So who's got the electrons? It's basically what that's saying to it right there. There it is again. Something's going to have to change here in a minute. Okay, so the first one we have is sodium chloride. Sodium gave up its 1 valence electron to the chlorine. We now call it a chloride ion instead of just chlorine. We put the brackets around chlorine because it's got all of the electrons, and we put the -1 charge out beside it. Notice that the sodium has a plus, or a +1 charge beside it. Next one is potassium bromide. And again, potassium is in group 1 like sodium, so it has a similar chemical characteristic. And notice that bromine is one of the halogens in group 17, just like chlorine, and so they bond in the same way. Potassium gave up its 1 valence electron to bromine, and bromine took it. And now we've got brackets around all 8 of them saying, hey, bromine owns these guys. We've got a +1 beside the potassium and a -1 beside the bromine. And then we look at something like aluminum fluoride. So we've got 1 aluminum. We're going to stick that in the middle because it makes sense to put that 1 lone thing in the middle because they're going to take the electrons from around them. And in order to get aluminum is in group 15, it means it has 5 valence electrons. It needs, let me rephrase that. Aluminum has 3 valence electrons. It's a metal, and it's going to give away those valence electrons. And it's going to, in this case, Chlorine can only take one of them, so we have to have 3 of the chlorines, and we give one of those valence electrons to each of the chlorine atoms. So aluminum doesn't have any dots around it because there aren't any more valence. It gave up all its valence electrons, and so it's got a +3 charge right beside it. And then you'll notice that we've got 3 chlorines. The brackets are around the chlorines, and each one has a negative sign beside it to show this the -1 charge now. How does it become a -1 charge? Well, if it stole an electron from aluminum, then it's got one more negative charge, one more negative electron than it has positive protons. All right, covalent compounds are simpler. First one up here, I've got all 3 of these guys are bonding with hydrogen. And remember that hydrogen, it can't have an octet. It's too small. So its first orbit, which can hold 2 electrons, is stable when it has 2. So typically, hydrogen only has 1 valence electron, and it's unstable. When you can get it so it shares so that it has 2, it's stable. All the other ones have to have the octet, the 8. So here we have water, and the water has 1 oxygen and 2 hydrogens, so we stick oxygen in the middle. Typically, we find the one that's the most electronegative, and that goes in the middle. We have a chart in the book you can look on. But a lot of times the easiest way is to say which do we have the least amount of, and that's the one we're going to put in the middle. So hydrogen shares its 1 electron with oxygen, and the other hydrogen shares its other one. And oxygen started out with 6 valence electrons. So if you count right around the oxygen, it now has a total of 8. Looking at the next one, we have ammonia. You guys have all smelled ammonia before. Each one of those little hydrogens, let's see if I can get my pointer. Each one of those little hydrogens has its own electron that it's bringing to the table. And then nitrogen had 1, 2, 3, 4, 5 of its own. It's in group 15. And so together they're sharing, so nitrogen has 8. But again, hydrogen is so tiny. It can only have 2 valence electrons to be stable. And the last one down here is methane. Carbon always goes in the middle. And carbon has its individual 4, 1, 2, 3, 4. And hydrogen brings 1. And when they share, you have to have 4 of the hydrogens to bring in those 4 electrons for the carbon to share with it and make it stable. So this is what the Lewis dot structure looks like for covalent compounds. A lot easier to do the covalent compounds than it is the ionic compounds. Okay. How do we figure out how to make these Lewis structures? The first thing you have to do is know whether it's an ionic compound or a covalent compound. Non-metal to non-metal, covalent. Non-metal to metal, ionic. And those are the big dogs when we talk about trying to show the Lewis structures for these guys. Okay, so what if we have carbon disulfide? All right, we have 1 carbon, and di is 2, so we have 1 carbon and 2 sulfurs. It's a non-metal. Carbon's a non-metal, and sulfur's a non-metal, so it's a covalent compound. Check the electronegativity. Again, kind of a cheater way to do it is to say, hey, look, we've got 1 carbon and 2 sulfurs, so we're going to stick the carbon in the middle. The less electronegative element goes first when you write the formula. So we have CS2. Oh, I backtracked. I didn't show you how to write that one. But the carbon has its 4 electrons, and it's going to share with the sulfur, which it has. Each of the sulfurs has 6 valence electrons. Now, we haven't talked about double bonds. Yes, we did. We talked a little bit about double bonds in one of the first two videos, and so you would have double bonds like the carbon dioxide. Sulfur and oxygen are in the same group on the periodic table, so they're going to bond with carbon in the same way. When there's more than one way to arrange the atoms, we call it resonance. So look below where we have carbon with the 3 oxygens there, and notice that you've got a double bond. Notice there are 4 dots between one of the carbons and the oxygens, but you could put that double bond in several different places. And so, which one's correct? And the answer is they're all correct because they all happen. And what they say is they call that resonance. So CO3, the -2 sign, CO3 is a polyatomic ion, which means you've got some pieces that kind of stay together as chunks. They call it a carbonate because it tends to that CO3, they tend to stay together. But they'll bond, that chunk of nonmetals will bond with a metal to form some